Welcome, everyone, to For the Love of Physics. And a special hello today if you're tuning in from Ishik Boys High School, especially Mr. Jager's class. We're really glad you're here. Today, we're doing a deep dive into something, well, really fundamental. It's how physics actually speaks the language of mathematics. And this isn't just about, doing sums or calculations. It's about how math helps us understand, organize, and even predict what's going on in the world around us. Think of it like physics' secret code.
That's a great way to put it. And for you listening, especially students, think of this as a bit of a shortcut. We're aiming to help you master some really key tools you'll see again and again in your textbook. We're going to break down how things like tables, graphs, and equations aren't just abstract ideas on a page. They're actually powerful lenses, ways to see and interpret what's happening physically. And we'll show you why getting concepts like dimensional analysis and even just quick order of magnitude checks will genuinely make your whole physics journey feel, well, a lot smoother.
Okay, let's unpack that because, when I first opened a physics book, all I saw were equations. And honestly, it just looked complicated. Is all that math really necessary? Or is it just physicists trying to, make things harder? What's the real reason it's so central to physics?
That's a really fair question, and the answer is actually quite elegant, I think. You know how scientists build models, simplified versions of reality to help understand it?
Right, like drawing a diagram of something complex.
Exactly. Well, math is the tool they use to analyze what they observe in those models, or in experiments, and to summarize all the data they collect. The big goal, really, is to find clear relationships. How does one physical thing affect another? And once you've sort of nailed down that relationship mathematically, the really powerful part is you can use it to predict what might happen in situations you haven't tested yet. So math helps describe those relationships, whether measured or predicted, with incredible precision.
Okay, so let's imagine you're actually doing an experiment, maybe in class or even at home. You end up with all this raw data, just a pile of numbers. It can feel a bit much. What's the very first thing you do to start making sense of it all?
Right. The very first step, and it's maybe more important than people realize, is just getting organized. And one of the simplest, most effective ways is using a table.
A table. Okay, yeah. Like if you were doing that classic experiment, the dropped ball one. So you drop two different balls, maybe a light ping pong ball and a heavier golf ball. And you do it at the same time in a vacuum chamber.
Ah, yes, removing air resistance. Good point. So you're focusing just on gravity's effect, like Galileo was thinking about.
Exactly. And you record how far each ball falls over certain time intervals.
And what you'd find, maybe using data like in Table 1.8 in some textbooks, is pretty amazing. Like after maybe 0.067 seconds, both the golf ball and the table tennis ball fall pretty much the same distance, maybe about 2.2 centimeters.
Huh. Even though they have different weights?
Even though they have different masses, yes. And then maybe at 0.2 seconds, they both fall around 19.6 centimeters. Putting these numbers side by side in a table, maybe time in one column, distance for ball one in the next, distance for ball two, it makes the pattern jump out.
Yeah, you can immediately spot that trend, right? The longer the time, the farther they fall. It's simple, but seeing it laid out helps. Like if you were tracking, your free throws in basketball practice, how many you make each minute. Putting it in a table just organizes the chaos.
Exactly. Tables are fantastic for that initial organization, but often the real aha moment comes when you visualize it. That's where graphs come in.
Right. So taking that same dropped ball data, time and distance, and plotting it.
Yes. If you plot distance on one axis, say the vertical y-axis, and time on the horizontal x-axis, like in Figure 112 you might see in your book, suddenly that pattern becomes visually obvious. You don't just see numbers, you see the shape of the relationship.
Totally. You can often draw a nice smooth curve connecting the data points, and that curve tells the story instantly. It's like looking at a fitness tracker app on your phone, right? You see the graph of your steps per day for the whole month. You immediately see the ups and downs, the trends, way better than a list of 30 numbers.
Precisely. And that smooth curve on the graph does something else too. It lets you estimate. Say you didn't measure the distance at exactly 0.225 seconds. You could look at your curve, find 0.225 on the time axis, go up to the curve, and read across to estimate the distance.
Ah, okay. Interpolating.
Exactly. But even more fundamentally, the shape of the graph is telling you something crucial. In the case of the falling balls, it's not a straight line, it's a curve. And that specific curve tells a physicist that the distance the balls fall depends on the square of the time.
The square of the time. Okay, that's a deeper insight just from the shape.
It is.
So we've got tables for organizing, graphs for visualizing. Is there a way to boil all of this down even further, like the absolute essence of the relationship, something super compact and powerful?
Yes, absolutely. That is the power of the equation. For that drop ball experiment, the relationship we saw in the table and the graph can be summarized beautifully by one equation. It looks something like this. The change in position in meters equals 4.9 times the time of fall in seconds squared.
Wow. Okay, change in position in meters times a 4.9x time of fall in seconds too. That's incredibly concise.
It is. That single line of math captures the entire behavior you observed. It lets you reproduce the graph, predict the distance for any time you plug in.
It's like the ultimate summary.
Right.
A tiny package holding all that information. You can predict exactly how far something falls just by knowing the time. That feels powerful.
It really is. And it's important to remember as you move forward in physics that many of the most important equations don't actually contain specific numbers like that 4.9. Often they just show the relationship between quantities in general terms. They're a compact statement based on a scientific model, showing how different variables are connected.
Okay, so we have these powerful equations, but let's be honest, sometimes they look like alphabet soup. You know, just a jumble of letters and symbols. I remember seeing things like V and Ek and Ek, and just thinking, what does it all mean? It can feel a bit like learning a new language.
It kind of is in a way, but it's a very logical language. Physicists use those letters as shorthand to keep the expressions simple and universal. So yeah, EVE is very often used for velocity or speed, keeps things brief.
And you mentioned Greek letters too.
Yes, a few common ones pop up, like the Greek letter A, that's delta. It almost always means change in or difference in something.
Never change yet.
And another one you'll see is A, that's the capital sigma. It means sum of or total.
Right, so that drop ball equation we had, change in position in meters, equals 4.9x, time of fall in seconds too.
We could write that using symbols?
You could, you might write it as AA 4.92.
Ah, okay, so E means the change in Y, the vertical position.
That's right, how far it's moved vertically from where it started. And Kate means the change in time or just the time interval that's passed.
Exactly. Kate is the elapsed time. See how much shorter and cleaner that is. D equals 4.92. It packs in all that meaning.
It does. And it's not just the quantities like position or time that get symbols, right? The units do too.
Absolutely. We abbreviate units all the time. M for meters, S for seconds, kg for kilograms.
So you might see in a table, like table 1 to 9 in a textbook, symbols like X or A representing change in position, and the unit listed next to them is M for meters.
Or with the unit S for seconds. Or M for mass with the unit kg for kilograms.
It seems like getting all these symbols straight is pretty important.
It's absolutely crucial. This standardization of symbols for quantities and abbreviations for units, it's what allows scientists everywhere to understand each other's work. Imagine if everyone used different letters for speed or different symbols for meters. It would be impossible to communicate effectively.
Yeah, total chaos. So it's like a shared global language for physics.
Precisely. It ensures clarity and avoids confusion.
Okay, that makes sense. So let's say you've got an equation now. You understand the symbols.
Yeah.
But how do you know if you've even set up the problem correctly, especially when things get more complicated? Is there a way to check yourself before you go too far down the wrong path?
Yes, there is. And it's an incredibly useful tool called dimensional analysis.
Dimensional analysis. Okay, what's that about?
It's basically a procedure where you treat the fundamental dimensions like length, L, time t, and mass, m, as algebraic quantities, like variables in math. There are two key rules. First, you can only add or subtract quantities if they have the same dimensions. You can't add meters to seconds, right?
Right, that wouldn't make sense. Apples and oranges.
Exactly. And second, for any valid physics equation, the dimensions on both sides of the equals sign must be the same.
Okay, the dimensions have to match on both sides. How does that help check things?
Let's take a real-world example. Say you're driving a car, like in figure 113 maybe. You're going at a steady speed of 88 kilometers per hour.
Okay, 88 kilometer, that's a speed. Dimensionally, that's length divided by time, LT.
Perfect. And you want to know how long it will take you to travel 725 kilometers?
725 kilometers. That's a distance, so its dimension is just length, L. And we're trying to find a time which has the dimension of time, T.
Right. Now, suppose you weren't sure how to calculate the time, maybe you guess incorrectly that you should multiply the speed by the distance.
Okay, so speed times distance. Dimensionally, that would be LT multiplied by L.
And what does that give you?
L times L is L squared. So L squared divided by T, L2T, kilometers squared per hour.
Is that a dimension of time?
Definitely not. So
Well,
just by looking at the dimensions, we know multiplying speed by distance is the wrong way to find time. That's actually really neat.
It is. It stops you right there. So what should you do to get time?
Well, if speed is lt and distance is L, and I want to end up with t, maybe I should divide the distance by the speed.
Let's check the dimensions. Distance L divided by speed LT.
Okay, L divided by LT. When you divide by a fraction, you multiply by the reciprocal. So L times TL.
And what happens?
The L's cancel out, and I'm left with just t time.
Bingo. So, dimensionally, distance divided by speed gives you time, which is what you wanted.
So the calculation should be 725 kilometers divided by 88 kilometers per hour. The kilometers unit cancels, leaving hours.
Exactly. And if you do the math, 725 divided by 88 is about 8.2. So 8.2 hours.
That makes total sense. It's like if you're baking and the recipe needs cups of flour, dimensional analysis stops you from trying to add, I don't know, cups of seconds. It just flags that something's dimensionally wrong.
That's a great way to think about it. Even for a simple problem like the car trip, it's a good check. But when you get to more complex physics problems, dimensional analysis is often a really wise first step. It can save you a ton of time by catching fundamental setup errors early on.
Okay, that's a super useful tool. Now, what about situations where you don't need the exact answer down to the decimal point? Maybe you just want a quick check to see if your detailed calculation is even like in the right ballpark, or you need a rough estimate really fast.
Ah, yes. That's where order of magnitude calculations come in. They are incredibly handy.
Order of magnitude. Sounds fancy. What does it mean?
It's basically about finding the power of 10 that's closest to the actual number. So instead of dealing with 725, you'd think about what power of 10 it's nearest to.
Okay, so 725, that's between 100, which is 10 innards, and 1,000, which is 10 innards. It's closer to 1,000. So the order of magnitude is 10 innards.
Exactly. And why is this useful? Well, two main reasons. First, you can quickly estimate an answer before you do the detailed calculation just to get a feel for the scale. And second, after you've done the exact calculation, you can compare it to your order of magnitude estimate to see if your precise answer seems reasonable. It's a great sanity check.
Okay, let's try with our car trip again. We had 725 kilometers and 88 kilometers.
Right, so 725 kilometers, as you said, is roughly 10 man-kilometers.
And 88 kilometers, well, that's pretty close to 100 kilometers, which is 10 minute or kilometer.
Good. So we want time, which we found is distance divided by speed. Our order of magnitude estimate would be 10 linear kilometers divided by 10 linear.
Okay, dividing powers of 10, you subtract the exponents, so 3 minus 2 is 1. That gives 10 innards.
Which is just 10 hours.
And our exact answer was 8.2 hours. So 10 hours is definitely in the right ballpark. It tells us the answer should be around 10, not around 1 or 100.
Precisely. It gives you confidence that your 8.2 hours is likely correct. It fits the scale.
That seems really useful for quickly checking work. Can you use it for, like, much bigger estimations too?
Oh, absolutely. That's where it really shines. Imagine trying to estimate something huge like how many liters of gasoline are used by all the cars in a country in a whole year. Say, southern Kurdistan.
Whoa. Okay, that sounds possible to know exactly without tons of data. How would you even start to estimate that?
You'd break it down using order of magnitude thinking. First, population. Southern Kurdistan is roughly, let's say, 5 million people. That's 5 by 10 ELO.
Okay, now how many cars? Maybe guess. 1 car for every 5 people, as a rough average.
That sounds like a reasonable starting guess. So 5 million people divided by 5 people per car gives you 1 million cars. Order of magnitude 10 EO cars.
All right, 10 AO cars. Now, how far does each car drive in a year? That must vary wildly.
It does. Some drive maybe 10,000 kilometers, some maybe 30,000 kilometers or more. A reasonable middle ground for an estimate might be 20,000 kilometers per year.
20,000. That's 2 by 10 kilometers per year.
Okay, now fuel efficiency. Again, it varies. Let's make an estimate. Maybe cars average, say, 100 kilometers for every 20 liters of gasoline.
Okay, 100 kilometers per 20 hours. So how many liters does 1 car use per year?
We estimated 2 by 10 kilometers per car per year, and they use 20 L's for every 100 kilometers. So we calculate 2 by 10 L per car times 20 L 100 kilometers.
Let's see, the kilometer units cancel. 100 is 0.2. So 0.2 times 2 by 10 yellows, that's 0.4 by 10 yellows, or 4 by 10 yellows per car per year. So 4,000 liters per car.
Good. Now the final step. Total consumption for all cars. We take the liters per car per year, 4 by 10 yellow, and multiply by the number of cars.
Okay, 4 by 10 yellow times 10 yellow, multiply the numbers, add the exponents, that's 4 by 10 yellows per year.
4 billion liters. It's a huge number, but we got an estimate. Now, we have to acknowledge this is rough.
Yeah, we didn't account for trucks, buses, maybe families with multiple cars.
Exactly. So our estimate might be a bit low. But the point is, order of magnitude calculation gave us a reasonable sense of the scale. We know it's likely billions of liters, not millions or trillions.
That's actually amazing. It lets you tackle these massive questions and get a sensible feel for the answer, even with limited data. It's like having numerical intuition.
That's a perfect way to describe it. It's about understanding the scale of things, which is so important in physics, dealing with the very large and the very small.
So wrapping things up for today's deep dive, we've really seen how math isn't just numbers. It's truly the language physics uses to describe the universe. We looked at how tables get us organized, graphs let us see the patterns visually, and equations provide that ultimate powerful summary for making predictions. And we touched on the importance of symbols and units as the common vocabulary of physics.
That's right. And then we focused on two really practical tools for you to use. Dimensional analysis, that essential check to make sure your equations even make sense dimensionally, and order of magnitude calculations for getting those quick estimates and checking if your answers are reasonable. These aren't just things to memorize for a test. They are genuine thinking tools that will help you solve problems more effectively, both in physics class and honestly in lots of other situations too.
Definitely. So here's something to think about. Next time you face a problem, maybe even a math problem outside of physics, how could thinking about the dimensions involved help you figure out the right approach? Or maybe think about another everyday situation where making a quick order of magnitude guess would be really helpful. Stay in contact with your physics teacher. Stay creative